Okay, I think we're on. Oops. Spoilers. Okay, so welcome to the reinforcement learning workshop. This workshop was done as part of a project that we did for a client. The client wanted to know more about the solutions we were implementing. And so we did this as an introduction for management and also for technical people about reinforcement learning. So it's going to have some introductory examples of what is exactly reinforcement learning, and then we will go into a more technical part so you can see how it is implemented. So basically, we're going to have an intro with an example, also some other use cases. We'll take a look at a bit of the theory and the tools that we use to solve reinforcement learning problems. And then we'll go into the methods. And instead of doing the demo at the end, I'll do the demo for each of the methods as we go through them. But in this case, we only do value iteration, Q-learning, and deep Q-learning, because AlphaZero is substantially more complicated. So we'll go through a Colab notebook, and I'll share that notebook so you can go look at it at the end. Or actually, let me just share the notebook already, so you can follow it and take a look at some parts if you want. Let me know if you can access the notebook, by the way, or if you can't. So let's make a quick introduction to reinforcement learning. So let's say you have a robot car, and this robot car can be in one of three states. So it can be cool, warm, or overheated. And if it's overheated, it can't travel anymore. And so as it is cool or warm, you get to choose if the car can go slow or fast. And the objective here is that you go as further as possible in a certain time. So if you go fast, you always gain, let's say, 2 units of distance. That's why there's a +2 here. And if you go slow, you always gain 1 unit of distance. So you gain less distance. And this is the case both if you are cool or warm. And let's say if you overheat, you lose 10 points. And so this means that it's really bad because you can't finish your journey, let's say. So in this case, you have a sort of reward system. You have states, and you have actions that take you from a state to another, and then that can produce the rewards. And so basically the problem here would be, how would you choose action at each state? So if you're cool, should you go fast or should you go slow? And if you are warm, should you go fast or should you go slow? In this case, you also have some probabilities associated. So let's say if you're cool and you decide to go slow, you have a 100% probability of staying cool. But if you go fast, you have a 50% chance of getting warm and a 50% chance of getting cool. And same if you are warm, if you decide to go fast, you have a 100% probability of overheating. And if you decide to go slow, you have a 50% chance of going cool, of becoming cool, or a 50% chance of staying hot or warm. So this is a question for you. How would you decide for each of the states? which action to take. So let's say you start with a cool car. What should you do to travel as further as possible? Someone? Careful, too many answers at the same time. What should you do if you're cool? Anyone, please answer.
Just go fast.
You should go fast.
Yeah, you should go fast because you gain more distance, and the objective is to gain as much distance as possible. And if you are warm, what should you do?
Go slow.
Yeah, you should go slow because if you decide to go fast, you will overheat. You should always go slow if you are warm, and you should always go fast if you are cool. And that way you maximize the points that you get or the distance that you travel. And so basically you just solved a reinforcement learning problem, or at least a very basic Markov decision process, which is basically the basis for reinforcement learning algorithms. So basically reinforcement learning is the science of learning to make decisions. It's usually modeled as an agent which can do actions on an environment, and it gets feedback in the form of a reward and also a new state that it will get into. So given a state S, the agent does an action A and gets into a state S plus 1, S of t plus 1. So at the beginning, it starts at t equals 0, state S0, picks an action A0. This action is chosen by a policy, which is a function of the agent, or an internal function of the agent. And so this policy, based on the state, picks the action. And as a result of the evolution of the environment, the agent moves to state S1 and receives a reward R1. And this continues. So generally at state ST, you do an action AT, which equals pi, which is the policy of ST. It leads to a new state ST plus 1 and produces a reward R of t plus 1. And so the objective of reinforcement learning is to build agents that learn a policy that maximizes the rewards that the agent will get over time. This might seem very simple, but it can actually be applied in many different areas. One of them that we'll explore are toy problems. So this can be simple grid-like worlds or some simulations, as you can see here, of games. This could even be multiplayer games. More games includes video games, chess and Go, and even more complex video games that can be solved using the same framework. This can also be applied to robotics, to manipulate objects using robotic arms. On the web, can be used, for example, to suggest ads or suggest posts, and also figure out when to send a notification so that the user is more likely to pick up the phone and click the notification. And it can also be used for power management, for example, to decide when to produce power based on the demand. Also, as a part of the optimization algorithm for computational fluid dynamics algorithms, for self-driving, for example, for picking up or picking treatments or drug treatments for patients. This often involves choosing a sequence of drugs that the patients should take. And so it can be solved using reinforcement learning. For example, also for asset management or portfolio management, because this involves decisions that have an effect over time. And also, for example, for combat automation. So let's properly define the problem of reinforcement learning. And more concretely, reinforcement learning is mostly thought of in terms of Markov decision processes, or they are modeled as a Markov decision process. And this is defined as a tuple. That's basically just a set which contains a set of states which the agent can be in, a set of actions that the agent can take in at each state. The probability that the agent moves to a next state given that it is on a certain state and did a certain action. And this we call the transition probability kernel. A reward model, which is basically the reward that the agent gets by being in state S and doing action A. And also this a discount factor, which is between 0 and 1, and basically serves to calculate a goal. So, and this goal would be this sum of rewards, RT, discounted by the discount factor raised to the power T. So rewards that are given in the future are worth less than rewards that are received right now, because this gamma to the T will be smaller for later rewards. So basically, we want to find a policy, pi of S, of the state, that maximizes this goal. And here you can see a diagram of all of this, how you can think of all of this. So for example, you have actions, each action triggers a reward, or actually each action has a probability of leading you to a different state. And also you can get rewards based on this. So let's take a look now at the policy function and understand what this is. This can be any function, but you can think of it almost as just a table. You have a state and you have a corresponding action for that state. And this is basically just a mapping. The policy that we found earlier was that if the car is cool, we go fast. And if the car is warm, we go slow. If the car is overheated, it doesn't matter because we lost already. So a policy is just this. It's a mapping from states to actions. You can think of it as a function, basically. And from this, we can construct something that is called the value function. And this basically is given a policy, pi, we can find the value function, which is the expected value of our goal, so the sum of discounted rewards, given that we start in the state S and then follow the policy pi. So let's say in our toy example that the time horizon is 3 and the discount factor is 1, so it's basically irrelevant. You can cut it out of the equation. If you, let's say, start on state S, which is cool, if your policy is to always go slow, no matter what, then your value function, you'll start cool, so you'll always stay cool. And so you gain 3 kilometers in distance, for example. And so your value function would be 3. If you start warm and then always go slow, you will also only gain 3 kilometers maximum. You could actually stay always warm, or you could stay warm for a bit and then go cool. But in the end, you are always going slow. So because of your policies, so in the end, your value is 3 for this particular policy, which is always going slow. If we now take a look at the policy that we found, which is to go fast when the car is cool and to go slow when the car is warm, we can see that if we start with a cool car and follow the policy, the expected value, so if you take into account all of the probabilities that you have of becoming warm or going back to cool and then becoming warm again, or staying always cool, for example. If you stay always cool and go fast, there's a chance that that can happen. And so you would gain 6 kilometers, basically. Or it could stay cool 2 times and then go warm at the end, but you would still gain 6 kilometers. And so if you take these all on average, you will gain 4.75. It's less than 6 because if you go warm, then you have to go slow. And so it's less than 6. It can't be 6 exactly because of this reason. But you can see that it's a higher value than if you just go slow all the time. And same if you start warm. At the beginning, you would have to go slow, but then you have a chance to make it up by going fast again. And so the expected value here would be 4 kilometers. And so you can see already that this policy is better than the previous one, for which the value function was always 3. If you now take a look at the policy of always going fast, you can see that the values are negative because there's a high chance that you'll end up overheating. And so you can see that different policies produce different value functions. And we can take a look or interpret this in a more visual way. Let's say you have, for example, a grid world in which when we step from the square to the green square, you gain 10 points. But then each step along the way that you go through, you lose 1 point. So you lose 1 point here, you lose 1 point here, and then gain 10 here. So if we take a look at the value function on each of these states, you see that here it's 10 because if you follow the best policy, this is in the case of the best policy, by the way. If you follow the best policy, you end up gaining 10 points. Here it's 9 because you lose 1, and then you gain 10. Here it's 8 because you lose 2 along the way, and then you gain 10. So you can see that basically the value function here tells you how close you are to the objective. This doesn't need to be discrete, so you can have this in a continuous game, for example, golf, and you have the same mechanisms here, but here you don't gain anything by scoring the ball, but you lose points along the way. So basically, the value function just tells you how far away you are from the objective in negative terms. So how much you're missing until the objective. And this also doesn't need to, the game doesn't need to be probabilistic. You have an expected value here. That's because the game, for example, like the car, it's not deterministic whether you go warm or cool after you do an action. And so, for example, here, this is called actually I forgot the name, the Frozen Lake game. It's basically you have to traverse a lake, but you can, every time you move, you can slip sideways and end up in a hole. So there's like a 33% chance of going in the direction that you want, and then 33% chance of going either side. And you can do the same thing. You can calculate a value function for this game for any policy that you have. In this case, this is for the optimal policy, and you can see that the value here is bigger because you gain 1 point when you reach here. And here it's negative because there's a high chance that you might end up in a hole and you lose 1 point there. So this is basically one of the most important tools that we have for reinforcement learning. And most algorithms are built on this. And so finally, we have a state action function, which is similar to the value function, except that we condition also on the first action. And that's an input to the state action value function. So basically, this is the state action value function, which is a function of the state and the action, and an action, is basically the expected reward, or the sum of discounted rewards. If you start on state S, do action A immediately, and then from then on follow policy pi. And we can see here more examples. If you start cool and then go slow, and then follow pi, your, let's say here, oh yeah, here pi would be to always go slow. So if you start slow, you will always go slow, so you do 3. If you start fast and then always go slow, you do 4. If you start warm and goes always slow, you end up doing 3 also. And if you start warm and go fast at the beginning, you overheat. If you now take a look at the optimal policy that we found, we can see that here, if we start cool and go cool and then go slow and then follow the policy, the first time we only do 1, but then the policy tells us to go fast, and so we end up gaining more points. If we start fast, this is part of the policy, so this value is the same that we saw before. Same for this one. If we are warm, the policy tells us to go slow, so we do 4 kilometers of expected distance. And the same thing as before, if we are warm and we go fast, we lose 10 points. So you can see here different examples of the state action value function. And this is basically what we use to build algorithms. This function can also be called the Q function, which is sometimes referred as the quality function also, or the action quality. And you can think of it as a table, usually. Let's say you have for the Frozen Lake game. And this is the example that we'll see in the demo also, by the way. For the Frozen Lake game, you have, for example, 16 states here. And so the Q function, or you can also call it the Q table in this discrete case, it's basically for each of the states and for each of the actions, you get a value of the, so this would be the state action value. And basically Q-learning, which is a reinforcement learning method, it's just about learning this table for the optimal policy pi. And deep Q-learning, which is a term that you hear a lot, is basically a way to replace this table with a neural network. So instead of feeding in a state and an action and getting a Q value, you just feed in the state and then get Q values for each of the actions. But basically, it's the same thing. You can think of this as a function, and basically neural networks serve to approximate functions. So last theory concept that we'll see here is the Bellman optimality equation. So the objective of reinforcement learning is basically to find an optimal policy that we call pi star that maximizes the values in the state action value function. And so let's assume that we have an optimal Q table or an optimal Q function, which we call Q star. We know that there's a recursive relation for this Q star, which is called the Bellman optimality equation. I'm just putting it here. I'm not putting the derivation, but you can easily find it online, and it's not that complicated. So basically, by definition, Q of SA would be the expected value of the goal conditioned on the state, the first action, and the policy. if we want Q star, the optimal Q function, then we put here the pi star, the optimal policy. This step is straightforward, and basically to get here, you basically just extract the first term of this sum, and you end up with something similar to this. So you extract the first term, the sum is infinite, so you end up being able to find Q star of S prime and A prime, which is the next state and the next action that you will do on that state. And so if you just take a look at this, it seems a bit odd why we would do this. And it's a bit difficult to interpret at first, but I can give you some visual examples. So as before, we have this grid world where you lose 1 point every step and gain at the end. And if you want to, we can check this equation here. These values, you can think of them as the action value, state action values for each state for the best action that you can take. And so if we want to calculate, for example, the Q function here, we first need to know the reward of being in this state and doing the best action. So doing this in this state, the reward that you get from moving here is -1. Let's assume gamma is 1, or in this case, gamma is 1. The game is probabilistic, so this P is always 1 also. You always move to the state that you want to move. And any other state, the probability is 0. So if you decide to move here, you'll never end up in a different square. And you take the maximum of the value function on the next state, given that you take the next best action. So that would be the value here. So 9. The reward was -1. So the Q function here is 8. So basically 8 equals -1 plus 9. And this is true everywhere in this game. And this is actually true for any game that you can think of, or any Markov decision process that you imagine. Assuming that you have or this is true for the optimal policy Q, or the optimal Q function. So enough theory for the moment, or until the end. So let's take a look at the few methods that we have in reinforcement learning. Basically, what we've been exploring until now are Markov decision processes. And so the methods that we are going to use to solve these Markov decision processes have a way to be solved, which is called actually 2 ways. One of them is value iteration, and the other is policy iteration. But I'm just going to talk about value iteration because I find it more intuitive. And actually, one of them is a generalization of the other. So we'll take a look at value iteration, and then Q-learning, and then deep Q-learning. And these are the most widely used methods. And also, I'll also talk a bit about AlphaGo, which involves Monte Carlo tree search. So basically, value iteration. We basically, to arrive at the Q prime, which is what our goal is, we want to find Q prime. Once we have Q prime, we know the values of each action on each state. And so we can just choose the action with the highest value, and that will be the optimal action. In this case, for example, if you are on state 499, you see that the action with the highest value is going west. This is just a random example. And so if you always follow the best action, you know that you will be following the best policy, so pi star. And so basically the way to get to these values is to do a fixed point iteration on the Bellman optimality equation. So basically we have here the Bell optimality equation is basically this, but with Q star. So to get to Q star, we do fixed point iteration. So we start with an empty Q, so all zeros. And we start doing this at the beginning. These will all be zeros. So this is all zero. And so you just fill in the rewards for the states and actions where there are rewards. And then you start on the next iteration, there will be already some rewards here. So Q will not be zero everywhere. And so given the probabilities of landing on the places where there are rewards, you propagate the reward to the other states. And so if we do this enough times, we end up propagating the reward everywhere on the table. And this eventually converges into a set of numbers for that table. So once the iterations stop changing this table, we know that it converges to the optimal Q star. Because by definition, Q star, or by the theorem, Q star is where this equation is satisfied. And so pi star can just be found by choosing the biggest values on Q star. So let's take a look at this so it's more intuitive. Okay, so this is a Python note or a Colab notebook that I shared with you on the chat. I think you can see it, right? You got access to it.
Yeah, we can.
Okay, perfect. So I'm just going to go through some of these parts more quickly because they don't matter as much. This is basically just imports. This gem is the tool that we use to simulate these games. So in this case, we create an environment which is the frozen lake. And here is basically the problem that you saw in the image. You have a grid where there are holes in it, and you need to traverse this grid to get to a goal. But you have, for example, let's say you are on this square, you decide to move right. There's like a 33% chance of being here, 33% chance of moving right, and the 33% chance of trying to move up, but in that case you end up staying in the same place because you'll get out of the map. And so that's all those probabilities are basically coded or saved in the environment in this object P. And so this would be, in this case, we have, for example, an action space which is 4 actions, an observation space that is 16 actions, which is every state that you have. And P is basically a dictionary or like nested dictionaries. So for state 0, you do action 0, and this tells you the probabilities that you land on each of the states. So in this case, if you try to go left or up, you end up in state 0. You have a 33% chance of ending up in state 4, which would be this one. In this case, this is action 0 is trying to move left. And this basically tells you the reward that you get, and also if the game has ended or not. And if you go through this object, it's quite large, but basically, if you are here and try to move here, you get 1 point. And yeah, if you end up in a hole, I think you lose 1 point, and the game ends also. And also, if you get to the goal, the game ends. These are just some helper functions. Don't worry about them too much. It's just to print the policy, for example. So yeah, action 0 is to move left. So actions are encoded into integers. And this is where we start taking a look at value iteration. So basically, as I said, the Q table starts with zeros. So this is just an array of zeros with 16 by 4. And then you pass this into a function, and this function basically starts by copying the array, and then does a lot of iterations. And for each of those iterations, it goes through all the states and all the actions. It gets the outcomes of P, and so it initializes. So it sets the queue to 0 and then calculates a new queue based on the outcomes and also the value that was previously on queue. So actually weird, but okay. So for each of the outcomes that you saw before, you get the probability, the next state, the reward, and do the operation that I told you earlier, so the value iteration. If you remember, here the reward is outside of this sum. In this case, in the notebook, the reward is inside the sum because it's also dependent on the next state. So if the next state is a whole, the reward is -1. If it's not a whole, it's 0. And so here in this formula, the reward actually goes inside. But at the end, the formula is basically the same. And you calculate the new values for Q for each of the outcomes and for each of the states and actions. The residuals is basically the maximum difference that you have between the new array and the previous array, and then you copy one to the other. And if we run this, so here it printed the first Q. Okay, and then if we take a look, here is Q star, which is the Q that was found after all the iterations. Pi star is basically just the maximum of Q, or the maximum on the actions, the maximum value for the actions. And so you can take a look here. This is the map again, and this is basically the solution that it found. So you can see that the solution is a bit counterintuitive, but if you go through it, you understand why it has to be like this. So, for example, here you have a hole. You have a hole. So if you if you are, for example, on this square, and you try to move down, there's a 33% chance that you'll end up on the hole again. And so it's better to move left, because that way you'll either end up here, here, or stay here. And so you never fall into the hole. And basically this solution that it found is a way to use the walls to move somewhat safely through the holes and to get to the destination. And you can see by the residuals, we only needed 60 iterations to get to a difference between consecutive iterations that was very small. And so you can be pretty sure that this is the optimal solution. And actually, if we let this run for longer, the error decreases quadratically, I think, or at least in log space, it decreases linear. So this could go down to as much precision as you'd like. So yeah, basically it found this Q table. The places where there are zeros are the states that correspond to holes and also the goal. And we now have like an optimal policy. So this seems really simple, right?
Pedro, could you explain why the last arrow is pointed to left? Like,
okay. In this case, you see here that there are zeros. This arrow is meaningless. Whenever you end up in a terminal state, you never have to do another action again. So wherever there are holes here, for example, these arrows are meaningless because it tries to do the maximum across all of these zeros, and so it just chooses the first, which is left. I think that's what's happening here. Yeah, every hole and the goal have a left arrow because of this. Clear? Yeah. So basically, this seems really simple. The catch here is it is this simple because value iteration requires that you know the probability kernel. And so if you know the transition probability kernel, then you can apply value iteration and you can solve a reinforcement learning or a markup decision process really easily. But in practice, we almost never know the transition kernel. And also the number of states and actions that you have may be very large, or if you have a continuous problem, the number of states might be infinite. And so, yeah, as I said, states and actions may have continuous values. And so in this case, what would we do? So that's where Q-learning comes in. So if you know, you might have noticed that on the previous algorithm, we never did any of these kind of interactions with the game. We just looped through the probability kernel or the transition kernel and derived or calculated an action, a Q table that way. In practice, when we don't have the transition kernel, that's where we need to sample interactions with the environment. And so by interacting with the environment, we can gather tuples of state, action, reward, and next state. And basically, Q-learning uses the same Bellman optimality equation to learn the Q star, but instead of using the transition kernel, we use the tuples, so the interactions that we have with the environment. And if we take a look at the algorithm for Q-learning, basically instead of having the fixed point iteration, we have instead an update rule. And it's very similar to the Bellman optimality equation. Basically, this is the residual part of the Bellman optimality equation. This is the right term minus the left one. And you lose the sum over the possible next states with the probabilities. But the way this works is that each update that you do on Q will pull Q in the direction that minimizes this term. And so if we are minimizing this term, we are basically bringing Q closer to satisfying the Bellman optimality equation. And so the reason we drop we dropped here the probability kernel and the sum over the states that we had, just to remind you. We had this before. The new update, it's basically just R plus gamma max of Q, and you put this Q on the other side, so minus Q. That's what's here. And what replaces the probability kernel is basically the frequency with which you do the updates. So let's say you have more frequency of going from state S and action A to next state than an alternate state. Then that new state will be updated more often. And this is equivalent to having a higher probability in the kernel. And so this ends up being equivalent. I don't know if that's clear. This is a bit more difficult to conceptualize, but I hope that's somewhat clear. If you have questions, feel free to ask them.
And what is alpha here?
Okay, so alpha is basically the learning rate. Okay, if I just say it's the learning rate, it's easy for you to understand. It basically just controls the strength of the update.
Mhm.
And so I hope it's somewhat clear that this is basically equivalent to the previous method. Just instead of using the probability kernel, you replace this by sampling. And so if there's a high probability of going from one state to the next, that transition will be sampled more often. And so that's equivalent to having a higher probability value on the kernel for that transition. So basically now we can, we can now take a look at an implementation for this. Basically, there's another detail here. Since now we are sampling interactions with the environment, we need to start sampling somewhere with some kind of policy. And so we create what's called an epsilon greedy policy. And this basically means that this policy takes with 1 minus epsilon. Epsilon starts at 1, let's say. And so this policy basically starts by picking random actions. And as epsilon gets closer and closer to 0, the policy starts picking the best actions given the Q table. And so it basically just starts randomly and then starts using the Q table to do the best actions that it can. And yeah, that's basically how we start doing interactions with the environment. Like before, we start with an empty or a zeroed out array for Q. We define some parameters, the number of steps, alpha, gamma, and epsilon starts at 1. Then this means that the actions are random at the beginning. This is just a count to track the updates. We start by resetting the environment. We see here that at every million iterations or steps, we divide epsilon by 2. Also, we log the error every 100,000 steps. And so basically we have a state X. We calculate the next action A based on the epsilon greedy policy. We do a step on the environment. And then we do the update that we saw before. So that's what's here. You update Q by adding alpha times this term that you have here, which is R plus gamma max of Q minus Q. Where here the Q is the next state. It's Q of Y. So that's what you see here. It's R, you update it by adding R plus gamma max of Q on the next state. And this is the max over the actions. And you subtract the current Q value. And so basically, if we run this, you can see that it takes a lot longer now. Before we only did 60 iterations. Now we have to do like 5 million 5 million steps of the game to start improving. And so you can see that at the beginning we have some error. So the updates to the Q matrix are large, but as we train, the updates start being smaller, so our error starts decreasing. This will take some minutes. In the meantime, if you have any questions, feel free to ask them.
Hi. So I have a quick question. You didn't mention like Sarsa, I saw in the graph, but I have a quick thought that I really never figured out. Is that when do you choose using learning instead of Sarsa or vice versa?
That's a good question. So Sarsa and Qlearn, I don't remember the details of Sarsa. I know that you, instead of sampling just the next state, you also sample the next action,
Yeah, I
and
think so.
the update rule is different. Let me just
Yeah,
check.
it's a little different. It's really similar, but that's a little difference in the update rule.
Yeah, so the update rule, okay, instead of sampling with the maximum action, you sample with the actual next action that you took. I don't know how this impacts training, but it's basically very similar. Just the
Okay.
update rule that is slightly different.
Okay.
I mean, at the beginning, this might be more stable. I'm not sure. Yeah, I have no idea. I would have to look that up. But I can look that up and tell you another day.
Okay.
Any more questions? So basically, the goal of this whole workshop, not making you implement anything, but the goal is for you to go through the code, take a look at the equations that you have for the update rules, and then see how they are expressed in the code. That's basically the most important thing here. Then the rest, I think it's easier to understand the rest of the code. But this is really the core, and this is what makes the reinforcement learning part work. So this might have been finished. So yeah, so you have an error that's considerably decreased from the beginning. Still, it's not, we don't get to like 6 orders of magnitude smaller like before, because this method is less efficient. But in the end, if we take a look at the Q function that we learned and we take a look at the maximums, so the policy, we see that the policy is actually the same. Or actually, if we take a look, there's only one place where it's different, and it's in this square. So basically this one. And that's because there's holes in either side. So the optimal policy is to go either left or right into the holes, because that way, I'm not sure. Let's explain this in detail. So if you are stuck in this square and decide to go up, there's a 33% chance that you go up, and then 33 that you go into the hole, and 33 that you go into the other hole. So there's a 66% chance that you'll die. If you instead decide to go to the left, there's only a 33% chance that you die, and then you might end up in this square or this square. So it's actually better to try to move into the hole, because you have a higher chance of leaving. And so in this particular square that changed, that corresponds to this arrow. So moving left or moving right here is equivalent. And so that's why it figured out a different policy, but at the end they are both optimal. So yeah, here in this case, we just learned an optimal policy without having to use the transition probability. Is that clear? Do you have questions? Okay, so let's move on then. So basically this Q-learning, you can use it when you have a table. So you have discrete actions and discrete states, but you don't have the transition probability kernel. But we might go into a situation where the number of states is too big or it's continuous. And so in that case, you can't use Q-learning or SARSA for that matter. And so in those cases, that's when we get into deep Q-learning. So if your number of states is so large, you need to have a way to generalize across states. So you can have an output for each particular state. And so that's why we introduce neural networks. Neural networks are basically a way to generalize given like a sparse set of inputs. Deep neural networks can generalize to fill in the details. So if it's a continuous state space, you just sample some states in there, and then the neural network figures out the rest, or generalizes so that nearby states might have or probably have the same output or the same Q action value, Q value action. Okay, yeah, the same Q value basically. So yeah, basically here, instead of having that update rule that we saw before, we have something that is very similar. And we basically train the neural network to minimize a certain loss. And this loss is given, again, by an expression that resembles a lot the Bellman optimality equation. But instead of here, you have Q of S prime again, into the maximum over the next possible actions. But then here, Q is parameterized by the weight of the neural network, which we call theta. And so in this case, we try the loss function is given as a function of theta. And here Q is basically, we have basically two different copies of the same network, but in this case, we update this one and we let this one being fixed for some iterations. And only after some iterations, we update theta minus. This is what we call the target network, and this will just be the network. And this is basically just a way to make the training more stable. So the goal here is, again, to minimize this loss because we want to find a Q that satisfies the Bellman optimality equation. And again, instead of using the probability kernel, we do this by sampling tuples. So state action reward next state tuples. And so the loss function is given as an expected value based on the distribution of these tuples. And this basically just means that as you sample these tuples, you can do this update. And this actually can be done using batches. So what you usually do is that you collect a lot of these samples, and then you can do batch training and calculate this update, not only for a particular state and action, but for multiple tuples at the same time. And you'll see this in the code. So basically, the deep neural network is updated with gradient descent. So you calculate the gradient of the loss with respect to the parameters theta. And you also have a learning rate. And that way you keep updating the weights theta so that the Q function approximates the optimal Q function. Okay. So the code for this is a little bit more involved. Oh, basically, I forgot to mention, but here you have like a heat map for states that were visited more often. and which actions we did next. So you can see that the most visited state is the beginning, obviously. But yeah, basically just to be able to see something about the results. So on to deep Q-learning. We are going to use, I think it's PyTorch, yeah, for the neural network. In this case, since the frozen lake toy problem only has 16 spaces or 16 states, we did a variation of the frozen lake problem where the holes can be placed in random positions. And so in that case, you can't just memorize a policy for each of the 16 states. You need to have like a more general policy that can take as an input any map and predict the best action that can be done afterwards. And in that case, you have a number of states that is a lot larger. And so this would be a reason to use deep Q-learning. So we basically just wrote a wrapper for the frozen lake problem that creates like random maps. And basically the observation now, instead of being just an integer for the number of the state that you are at, now it's basically the map and also your position. So in this case, it created a map where the ones are holes. So you have holes in some places, and the minus ones are clear space or frozen lake, like frozen water. And this also, the second layer for this map is basically your position in the map. So in this case, the one represents where the agent is, and the minus ones are everywhere else. And so, yeah, basically this, we replaced the end. So every time you do a step, we now get a new state that looks like this, and you also get the reward if the state ended or if the game ended or not. And also, I guess this is a probability, but we will not use these probabilities. Don't worry about this. So yeah, we then built a neural network to handle this. This is basically an image with 2 channels and 4x4 pixels. So you can use a convolutional neural network to handle this. Takes 2 channels as an input. Why is this 60? We probably flatten this. No, it's 2D. Okay, I'm probably missing something. Sorry. So yeah, we built a neural network to handle these inputs. So this state or the format of the space of the state. I'll let you take a look at this by your own, because otherwise it's a bit too much. We also have a replay buffer. This is basically when you do interactions with the environment, you save them in the replay buffer, and then you can sample a batch of transitions, basically. So when you sample, it returns you a random sample from the buffer. Then the agent basically has a lot of built our internal code, but the most important thing here is basically every time it does a step, it adds it to the buffer. In this case, it's called memory, and then basically does a bunch of steps. I think I've set it to only do 1 step at the time. So basically, it alternates between doing a step on the environment and updating itself. So updating the weights of the neural network. And this gradient step is basically the update that I told you about before. You sample a batch from memory. First, you calculate the the activations of the target network. So this target network is basically a copy of the model. And so basically, first calculates the, in this case, it's the QI max. So this would be this part. I don't know why I can't. Okay, it would be this part. Then you calculate the delta, which would basically be all of this. So R plus gamma times QI max. And here it's just, in case the game ended, you don't do the QI max, you just add the final reward. So this would be 0. But you can, in practical terms, this would be, D would be 0 because you are almost never done with the game unless the game is finished. And so in the general case, this delta is basically the left part here. And then you calculate the activations of the model itself. And this criterion is basically the, let's see what it is. Okay, in this case, I use the hover loss, but it's similar to the mean squared error. So basically, you calculate the mean squared error between Q and this term here. And you try to minimize it. The error loss is equal. Once this is Q is close to, or once the error is close to 0, it's quadratic. But if it's larger, or if the norm of the error is larger than 1, then you stop having a squared sign here, and you just have an absolute, like a norm. And it's basically just in practical, like practically, it's like cutting or like clipping the gradients. It's just a different form of loss, but it's similar in nature. Oh, oops, sorry. Okay. So yeah, basically, you calculate all of these. You calculate the criterion, which is the loss, and then it's basically typical neural network stuff. You zero out the gradients. You do back propagation, and you update the weights. And by the way, is there anyone here who's not familiar with PyTorch and that doesn't understand this and that wants to understand it?
Well, I have never used PyTorch, to be honest.
Okay, what about TensorFlow?
I have used it, but yeah, like in general, I don't think it's worth like explaining just for me if everybody else understands what's going on.
Okay, but do you understand like neural networks?
Yeah.
Okay, so basically, this is a bit a convoluted way to do it, but this is how PyTorch does it. But basically, once you calculate the loss, this function will do a back propagation from the loss to all of the different weights and stores alongside the weight the gradient of the loss with respect to that weight. Don't know if that's clear. It's basically doing what I have here. It's basically this step. It's calculating this gradient, basically. And once you do optimizer step, it's when you actually does the whole update. But yeah, what you need to understand is basically these two functions are meant to do this.
Mm-hmm.
Okay, and yeah, that's basically it. So you end up doing this alternate step and then train. And then yeah, basically, like you go to the next transition. I'll let you go through this code by yourself, because it's easier than me just explaining this. So that's the reason I shared the notebook with you. Feel free to like copy it to your drives and experimenting with it, and running it yourselves, going through it. Yeah, but basically, this is some more helper functions. This is where we actually train. So basically here you can see that we start with like a random policy. This is just the random activations of the network when it was initialized. Let me just, yeah. Basically it's training now. You can see here some of the returns are -1 when it hits a hole. Some of them are 1 when it finishes. And you can see that the average, okay, this is weird because, let me rerun this actually, because this is weird. It started the first time it completed the puzzle. Okay, this is, I'm confused now. Okay, so okay. So yeah, the first episode that it did, it failed. And here you have like an average return of the episodes after that, and you'll see that this number starts out negative and will slowly increase. And that means that the episodes are finished more often, basically. So yeah, if we take a look at the network again, so basically at the end of it, we have the number of actions. And so it's basically what I said before here. The number of outputs of these neural networks, it's the number of possible actions that you have. So the network outputs a number for each of those actions. And what we see here is basically the maximum, or the maximum output of the network. So which action was at the highest value, and so that identifies the direction, and then we have that value here. And if you take a look, we can see that this number keeps increasing. Can take a look at the network again. I was actually confused by this 16. Oh, okay, no, sorry. Yeah, this convolution is meant to go from 2 channels to 16 channels, and it's a 3x3 convolution. And so it does one of those, and then it flattens. And since there are 16 channels, the length of the vector that you get here is 16 times the size squared. So this will be 16 again. And so there's a linear layer that goes from 16 squared to 128, and then from 128 to 4. Okay, that's it. Any questions about like the architecture of the network? All right. But yeah, that's basically it. If you can keep going here if you want, but basically this number is already positive, so means that we are on average finishing more times than we are failing. This usually increases up to like 0.5 or 0.6 at best, at least with my previous experiments. But you can see that the policy is still not very good. It's still like trying to learn a better policy. But we could be here for a long time. So if you have any questions, this is the time to ask them. This is basically the end of the workshop.
Yeah, if nobody asks, like, I have a question. Maybe it's dumb, but I believe there are no dumb questions, like when you learn something. So thank you for this review, but for me it seems right now that it's a bit like theoretical. You know, you use this GEM library to simulate environment, you interact with the environment, and by creating some env class, etc. And what to do if you deal like with the real world business problem? I don't know, you mentioned, for example, adding to your website, right? When you want to show the customers an ad and you want to learn like the best strategy to show in that app to start gaining some profits out of that ad as soon as possible. So what should be like the data gathered? What would be like the states here and the actions here? The actions, probably the clients clicking on that ad, yeah. But what about the states, and what would we feed into those neural networks?
Great question. So basically, when it comes to applying this in a real world, it's often up to you to decide what are the states and the actions. So it's important to have a taste for what that could look like. So for example, let's say the example here is knowing when to throw a notification to a user. In this case, the state would be, for example, a feature vector that could include the time of day. It could include when the user last logged in. It could include some other data gathered about the user last time, like the usage patterns of the application. Yeah, basically that's it. The action, as you mentioned, is when to throw a notification or not to throw a notification at each time you run it. And the reward is basically if the user clicked the notification, that's a positive reward, and if he didn't, or if he deleted it, it's a negative reward. And so basically, you can sample this every time you throw a notification. You can create one of those tuples and store it, and you can do this even without having trained the reinforcement learning algorithm. You can use some other strategy. Actually, now I remember the difference between Q-learning and SARSA. Sorry, I'll mention that in a bit. But yeah, basically with Q-learning, you can use any strategy to gather data, and so you could use any custom algorithm that you built before that, like a custom rule that you, for example, send notifications always when the user picks up the phone, or you send notifications always after 8 o'clock. You can do some sort of rule like this, or like even just show notifications at random times. That actually might be better. And see when the user picks up the phone and clicks the notification and when it doesn't. And you can store a bunch of tuples for these. And then you can use Q-learning to learn a strategy from the sample tuples. So you save the samples of the state when you send the notification, and whether the user clicked it or not. And you then can train the algorithm to do this. Or to figure out a strategy of when to send the notification to get the most reward, or so the most likelihood, the biggest likelihood of a user clicking it. Is that clear?
Yeah, more or less. And to perform this learning, you still will need like a rather big data set, right? For the real users.
Exactly.
Mm-hmm.
But yeah, luckily you can generate this data set before you train the algorithm. And then usually this involves an iterative process. So you train the algorithm, you deploy it. So now you have a new strategy for choosing the notifications. You generate more data with that, and then you rerun the training, then deploy it again. So it's a difficult process to implement in the production environment, but it is possible. And we've actually done it in our project, not in the production environment. It was in a development environment because the product never went into production. But yeah, we actually managed to implement a flow to do this completely autonomously. So we set up this group that gathers data, then trains a model, then deploys a model, gathers more data with the new model, and keeps doing this over and over.
Yeah, my
Yeah,
next
go ahead.
question, was to be about this real project, whether it was like finalized and you deployed it, but you already answered it. And one more question, like if this is like iterative process, how would you understand if you have if you need to implement more features, for example?
It's yeah. Were you going to say anything else?
Yeah, like whether you could, enhance your results by gathering some other features about your users, for example.
Yeah, in that case, it's very difficult to experiment with using new features, less features, exactly because your state could change, or at least let's say, yeah, unless you save all the possible features in the tuples that you might want to use, it's difficult to change. So the best strategy here would be you gather as much data as you could possibly, or as many features as you could possibly need for your state vector, and you save them in the tuple, and then you experiment in the training part with using some of those features or not using some of those features. So it is possible to do this, but you have to keep in mind that once you start building the data set of transitions, the tuples, if you need to add some new feature, you will need to rebuild that data set. You can't use the old one.
Yeah,
And
I
so
got you.
as a strategy, you should from the very beginning like save as many tuples or as many features in the tuples as you possibly can.
Pedro, if you
Yes.
like, if you want to add features, can you not like just save the the table, the transitions table, and then the queue in it created from scratch regarding that table? If you wanna if you wanna add features, you can create one using that.
Yeah, so I'm not sure I understood the question.
Maybe I'm misunderstanding the question from Irina, but if you're trying to add new features to the states, like you have 3 features, now you add more. So
Mhm.
the state that you have previously, the table, it's different dimensions and everything that comes with that. Can't you, like, in order to keep training the model, like create like a model from scratch, the table from scratch, but the table itself is based on the Q table that you had previously?
Yeah,
And
that's basically what you do. You first gather the tuples for every possible feature that you can use. But once you want to train an algorithm, you pick a subset of features and you build the table based on the combinations of those features. But most likely you would use a neural network and train the neural network only on those features.
okay.
Yeah, I think that was your question, or no?
More or less. Because I thought we were talking about like reinforcing the table itself. I never experienced with like deep learning, Q-learning, deep Q-learning. But
Mhm.
with traditional Q-learning, we could like just update not update, but create a different table with the states from scratch using the table that we had previously, and we could keep training using that.
Yeah, but that's basically it. You create the table from scratch, but you keep you build the table from the same data that you gathered before, even if you're just using a subset of the features.
Yeah.
Yeah, you can build a different table for each subset of features that you want to use.
Okay.
For different iterations of the algorithm. So yeah, and by the way, the difference between SARSA and Q-learning, I think it's that SARSA, if I'm not mistaken, is an online, not an online, on-policy algorithm. So SARSA basically requires you to only gather tuples that follow the particular policy that you have at the moment. I'm not, let me see if I can find it here. Oops. Yeah, this is a non-policy learning algorithm. This basically means that you can't use a different strategy to build data to train this algorithm. You need to always update it with the Q table that you have at the moment. So you can't turn this into a deep learning algorithm because that requires data from the past. This basically can only be trained
Okay.
with the updates that you just did. So you do an update, you do an so you do a step, you do an update, you do a step, you do an update.
Okay.
You can't use the replay buffer.
Okay. Got it.
And,
Thanks.
and so that's why Q-learning is so practical. And it's what's mostly used in real world applications. It's because you can gather data any way you want. And because there's a max here, the max operation on the actions, that turns the algorithm into an off-policy algorithm.
Okay. Got it.
Yeah.
Thanks.
No problem. So yeah, basically this continues to train. It's not doing as well as I thought, but it's getting there. As you may imagine, this takes a long time. But yeah, it's at the moment it's getting to the end, so the ones like way more often than losing. So this means that it's closer to optimal. I think in practice, this game you can never have a 100%. When you have a random map, you can never have a 100% success rate. But yeah, one more thing. For the presentation. Yeah, one more thing. I still have the part on AlphaZero. If you're curious, I'm gonna go through it rather quickly because I don't have like code to show it, but it's just for you to get some kind of intuition about how it works. So basically, AlphaZero, the key difference here is that it requires having a simulator of the environment. And so in the case of games, you can use it for example, chess or StarCraft, you can use AlphaZero. But in real world applications, it's way more difficult. Unless, for example, for robotics, you can have a simulation of the robot. But in most cases, it's difficult to have that kind of thing. But basically, AlphaZero basically is an evolution of the algorithms that were previously used to play chess, for example. These algorithms basically do a search on all the possible combinations that can be done, starting from a particular particular state. Basically picks the action, or picks basically the action that leads to the best future states, or that has a higher expected value. And Monte Carlo tree search is basically a way to do this tree search that has been widely used. And I'll let you search that for yourselves if you're interested. But basically for chess and Go, Monte Carlo tree search relies on, once you get to a state, you basically do random playouts until the end. So each player starts picking random actions because you have a way of determining what is the best action. Or you do like random actions until the end of the game. And then see if you won the game or lost. But for chess and Go, because the games are very long, this doesn't suffice. So you need to have a way of calculating the value of this position once you get there, instead of having to play the game until the end. And so basically AlphaZero is a sort of complicated way of using neural networks to predict the value of certain states. And also of predicting what is the next best, or what is the best action to do on certain states. It's basically two networks. There's like a value network and a policy network, and they basically approximate these two things. And it's basically a way of improving Monte Carlo tree search. So yeah, the random playout phase is replaced by an evaluation of the value function at that state. And the way you select which state you will evaluate next is basically using an approximation of the a policy function, which is modeled as a neural network. Both of them are modeled as a neural network. Yeah, so this is basically applied. Usually, when you see it's like more applied to two-player games like chess, but it can also be used easily for like single-player games or single-player problems, or like planning problems, basically. But yeah, that's basically it. The demo is, I have a link on the slides too, in case you lose it. And yeah, I'll send you the slides by email when we finish. Do you have any more questions about this? I know this is complicated. This is just like a brief introduction, so you get some sort of intuition of what AlphaZero entails. But I'll leave it up to you to research this further if you are interested. But yeah, any more questions? All right, I guess that's the end then. I'll stop presenting. So we're still alive. I mean, I'm
Yeah.
sorry if it was too technical. I mean,
No, like it was fine. What I'm curious about that project that you had. To which extent was the customer aware of reinforcement learning, and have you had to explain all those concepts to them, or there was a technical person from their side that could communicate on the same level as you do?
basically, there was no one on their side that was even at the level of understanding basic machine learning. There were technical people there, but they were mostly software developers.
Yeah,
And
what I'm curious about, how to explain this to business-oriented people, like in simple words, because even for me, I have never dealt with reinforcement learning, and it's like a dark forest for me right now. Like, of course, I understand where to start from your notebook, but still, like,
yeah, basically from their side, there was a lot of interest in understanding this stuff, at least from the software developers. And so that's why we did this workshop, and also another one on data science in general. But yeah, to explain this in simple terms, I guess the best advice that I can give is to look at the content that we've been writing for the website. So basically, we have a reinforcement learning section there. And what we said was reinforcement learning is basically to solve problems that require multiple interactions with an environment. And I think that's the most high level description that I can give. It's difficult to go in more detail without getting into technicalities. But yeah, basically the key here is that the only way that you can solve the problem is by interacting with something. And so you gather feedback from those interactions and can develop a strategy to have better interactions, basically, or to receive more reward, basically.
Okay, thank you.
Yeah, no problem. Any final questions before we leave? All right. Well, thank you, everyone. I see there are some comments here. Just a second. Yeah. Yeah. Alexandre, thank you for the link. I can check it out. This is basically a course on reinforcement learning. Alexandre.
Seems like it's for broad AI stuff. Should
AI in
include,
general.
yeah.
Okay, it's really cool.
Thanks for sharing.
Yeah, thank you. Well, thank you everyone for attending. I hope I didn't bore you too much with technicalities. Basically, the goal here was get a somewhat technical introduction. Because usually when I go to talks, when people introduce things like too generally, yeah, I usually go away more confused than before. It's better like to explain things in some detail, even if you might become confused at the beginning. Like at least you get a sense of what is involved, even if it's not clear, like all the different details. And so, yeah, that's the reason why I built that notebook. It's basically for you to explore and try it on yourselves, by yourselves. And I'd say once you understand everything that is in there, you understand basic reinforcement learning. Yeah, and you can even apply that. Basically, these type problems was exactly the implementation that we used on the project, the deep algorithm one. And so if you need to use reinforcement learning on the project, you might reuse some of this code also. But yeah, thank you everyone then. Glad you
Sorry,
made it.
one
Yeah.
quick question. Would this presentation be shared somewhere that we can look at it in case we want to like refresh on what we talked about?
Yeah, I'll send you the slides, also with a link to the collab notebook and also the recording of the
All right,
workshop.
perfect. Thank you.
All right. Well, thank you everyone. It was a pleasure.
Thank
Likewise.
you.
Thank you.
See you tomorrow.
Well,
Bye-bye.
Bye.
See you tomorrow. Bye bye. Have a nice day.